All right, since recording is in progress, I guess that means I best start talking. This is Roger. I'm going to be your presenter today. I guess my name is at the bottom of the page here. Let's talk about this. Is the fact that we say we're talking about an ethical challenge today. Ethics is always something that people often want to discuss. And questions are welcome. We're going to try to discuss whatever questions may come in, comments, whatever. What I'd like to ask, though, is that we've got two different communication means here. One of which is the Q&A, which I'd like to reserve for the class content and any comments or questions on class content. The chat is there for people to say hi to each other. If there's an issue with what's happening as far as reception or anything, that's the channel that our host is monitoring. So if you need to communicate with the host, do that in the chat channel if you would, and we'll do the rest in Q&A. I see we have 35 participants here, meaning it's not practical to try word type questions. So we do need you to type your questions in the Q&A. I get a little ding when the question comes in. I'll be watching that and doing my best to answer the questions that I see verbally. And we'll try to keep up that way. Okay. Now, the point here, fact and fiction of climate change problems and solutions, where we're going to be focusing today is the solutions that engineers and architects can be a part of over the next couple of decades. And of course, it's pretty hard to solve a problem unless you've defined the problem. We certainly see that every day. And by the way, I'd like to welcome my colleague who happened to join this webinar, who did an ethical thing of her own yesterday. And we at our company are all proud of Mindy for her work that she did. In any case, I want to identify some of the problems and make them pretty clear what some of the problems are. But we're going to focus on the solutions. Just if you want to read up on more of the problems, references will be there. And I'm going to flip through those kind of quickly so that we can focus on the solutions. Okay. So there's our rules of the game here. And so let's get on the move. Here's what we want to talk about. We want to talk about what's going on. How serious is it? We want to distinguish between fact and fiction. What can we do about it? What will it cost? And then we're going to get specific and talk about greener buildings, greener transportation, and greener government. And for that matter, some greener ethics. The interesting thing about the ethics here is that certain people are affected more than others by this whole climate change thing, and that turns it into an ethical issue. Okay, so let's get moving. And let's start with looking at some of the fiction. Most of these are things you've all heard of, that climate change is a hoax. Well, there are a whole lot of people who would disagree with that statement. It's often been said that climate change is not caused by humans. Well, there may be some disagreement, but I just happen to have read a whole lot of stuff and happen to believe humans are pretty responsible. And we'll see part of that as we move through where the human contributions have been made. Some people believe that and want to believe, really seriously want to believe that the change in climate right now is just a temporary deal and it'll be gone in a couple of years. And that if you look back into the 1800s, they had all these dust storms and droughts that lasted for 5 years, whatever. Well, okay, 5-year periods, we're looking at 200, 300, 400-year periods now. So it's quite a difference. Of course, if you're up in the Northeast where live webinars are required, well, I heard it's been actually pretty nice up there the last few days from our relatives up there. That Then there's others who will say the average temperature has not changed. It's just that they use a different definition of average. Even if you have an increase in temperature over the years, there's still an average temperature. And the problem is that average temperature does change every year as you add more. I tried applying this to my age, and I figure if my average age doesn't change either, it gradually goes up. But if I only take my average age between 2000 and 2020, my average age would be something in the order of 58 and or 68, something or whatever. In any case, all I have to do for each year that I add on the top end, I have to add another year on the low end, and I can stay at the same average age for quite a long time. And of course, there's sea level rise down where I am. Lots of folks are worried about sea level rise here in South Florida, and rightfully so. But that's not the only thing. And we're going to look at a couple other things as well, just to get an idea of what else is out there. Now, somebody said they actually can see my cursor. And so from time to time, I will be pointing some things out on the screen. And but for the most part, it's going to be pretty evident what we're talking about. It's first useful to make a distinction between weather and climate. What you see before you here is weather, and weather can sometimes be pretty nice, pretty interesting, and sometimes you want to stay inside. Anyway, you can go to definition of weather, and it's what's going on right now in a certain place. That's weather. And hot or cold, wet or dry, calm or clear, whatever. That's weather. That's what's going on right now. Climate, on the other hand, is a trend in the weather, whether it's getting wetter, drier, hotter, colder, whatever. If there's a trend from year over year that one of these things is changing, we're looking at basically, one would argue from an engineering standpoint, weather is the function itself, and climate is a derivative. And if the derivative of zero, that means the weather's not changing much. But if you have a derivative is positive, that indicates an increase in something. All right, so that's just a little engineering math. So you'll all be happy. There's your math for the day. Well, we'll do a little more later, maybe. What's the effect of greenhouse gases? Everybody knows that a lot of the greenhouse gases, mostly we think about carbon dioxide, but certainly methane has been getting a lot of attention lately, especially over at the big meeting in Europe. So let's just do a little factual information about global warming and its causes. Just so when you're at your Thanksgiving dinner and you start talking about global climate change, you can change the subject right away so you don't get into an argument. But in any case, if you get in with a group of folks who are interested, we can start with the idea that visible light is one form of short wavelength radiation, and that infrared is another form of radiation. It's just longer wavelengths. And we can observe that the Earth takes on radiation from the sun. And we can say that also acknowledge the Earth gives off heat at night and in the daytime, for that matter, in the form of infrared radiation. To maintain equilibrium, this should seem pretty obvious. The amount of heat absorbed by the planet every day, or at least on average, has to equal the amount given back. Otherwise, it's going to build up. I think most people recognize the atmosphere is transparent to most visible sunlight wavelengths. And that's why the sunlight is kind of this color of sunlight, because it's basically lets all the colors get through. On the other hand, the atmosphere greenhouse gases up there tend to reflect the emitted infrared radiation back to the surface again. And the more that are up there, the more that gets reflected back. And when that happens, then the Earth temperature has to rise a bit in order to restore equilibrium. Fortunately, radiation is proportional to the fourth temperature, the fourth power of the absolute temperature of the Earth. So it doesn't take a whole lot of increase to increase the re-radiating. On the other hand, it doesn't take a whole lot of increase to cause a whole lot of other problems. So therefore, here's a little background. And again, slides are available. And that way you can read through these again if you want to think about it a little more. It's always fun to play with Excel, especially when you've got a formula in hand, and when you've got the black body radiation formula, you can say, okay, here's the deal. The surface temperature of the sun happens to be about 5,800 K. The surface temperature of the Earth is around 300 K. And therefore, these are what the black body radiation curves look like for the sun and for the Earth. And notice they're on a log-log plot. So both scales are logarithmic. And notice then that the peak of the infrared radiation from the Earth is at about 10 to the minus 5 meters, or 10 microns, or 10,000, whatever units you want to use. Anyway, we're plotting wavelengths in meters. And you notice the peak of the sunlight is right down there around, let's see, the 0.98765, right around 500 nanometers, or 0.5 micron. And that's our nice yellowish orange light, which our eyes are most sensitive to that. And that's where sunlight peaks out. And that's why we now paint fire trucks, fire engines yellow instead of red, because our eyes are a little more sensitive to yellow than to red. Now, if we break down these spectrums, what's the part we can see? That's between the two blue lines here. That's the visible part. If we move off to the left, we see the ultraviolet, which we can't see, of course, but we can get a good sunburn from it. And in fact, if we put our COVID masks in an ultraviolet cage, we can disinfect them in there. So there's some good uses for ultraviolet. On the other side is the infrared. That's the stuff we can't see, but it's nice and warm. So here's the thing, that the sun, it travels about 93 million miles. And by the time it gets to the top of the Earth's atmosphere, its intensity is about 1,367 watts per square meter. Now, I know you're all going to want to memorize all these numbers, because after all, it's good dinner time conversation, of course, for engineers, as long as there's no non-engineers at the table. Otherwise, they tune out pretty fast. At the surface of the Earth, after this sunlight penetrates down through the atmosphere, it loses about a third of its intensity. And at the surface of the Earth, directly down with the sun straight overhead, the intensity is about 1,000 watts per square meter. And that's important because that happens to be the standard test condition for photovoltaic equipment, for example, and a lot of other things that base on the sun. It also gives a pretty good idea of how many total watts, and for that matter, how many watt hours, if you add it up for an hour, that are available from the sun. So if you take the whole area of the planet, lots of folks have done that, and they indicate that in about an hour, you get about a year's worth of energy in terms of the energy that we use. So, what about the carbon dioxide? I can remember way back, 40, 50 years ago, where I heard about the Mauna Loa Observatory, where out over there in Hawaii, where they're looking at upper atmospheric concentration of carbon dioxide and other various gases. And notice down in 1960, it's down around 310. And if you go back to 1943, when I was born, it's down below, I'm sorry, 315 in 1960, but it's down below 300 back in 1943. So in my lifetime, the atmospheric CO2 has increased by well over 100 parts per million. And percentage-wise, in terms of 400 parts per million and 100 parts per million, it's gone up by 25%. Well, is that good or bad? Well, we can look at some projections. If we keep doing what we're doing right now, we're looking at the red curve, number one. If we recognize that what the climate scientists are saying is that somewhere between 425 and 450, this exponential increase could become a runaway problem, and there may no longer be any way of stopping it until some nonlinearity comes into effect, whatever that might be. So notice that 425 is right about where that green one ends, number 3. And of course, number 4 is that which would happen if we today immediately eliminated all greenhouse gases. So what we're really looking at is what can we as engineers and architects do to contribute to trying to achieve this, the green curve number 3. Is it in fact realistic? Is it cost effective? How much is it going to cost? What can we do to help? So that's what we're looking at is number 3 here. How can we take a look at that? And of course, that's what folks over at the climate conference are looking at as well. How can we achieve that curve number 3 and stop this exponential increase? I'm going to go through these tipping points quickly because this addresses the idea that there's more to climate change than just sea level rise or polar bears floating on pieces of ice wishing they knew where their next meal was going to come from. And there's a lot of words here, okay, and I'm going to click through them quickly because once again, what we're concerned about is global warming becoming irreversible, and that can happen. That's what happens when a atomic bomb goes off, for example. The exponential process gets out of hand. You've all solved the math of the underdamped system where it all of a sudden just goes out and until there's a point where there's some nonlinearity that stops that. And we just aren't real sure what the linearity might be. So any of these things are certainly things we don't want for our grandchildren and great-grandchildren. I know of one person who has a 2-year-old, just turned 2 in the audience, and I have a great-grandchild who just turned 1, and that great-grandchild will hopefully be around in the year 2100, and I would like for him to have a nice planet to inherit, and I'm sure everybody as a part of this program here this morning has similar feelings about their following generations, and maybe for themselves, depending how old you might be. So tipping point number 1 is total atmospheric water vapor. Wow, we ever thought about clouds as being maybe a problem, but here's what happens. And as the planet gets hotter, we get more clouds, and more clouds means ultimately exponential increase in water vapor, and not all in the same place. Obviously, the folks in southwestern Colorado would love to have a little bit of this. But anyway, tipping point number 1 is atmospheric water vapor. And a lot of people don't think about that, but it happens every day. The thing about it, it works fast. When the clouds go away, when the water vapor decreases, then the effect is not so much. Then there's the total amount of melting ice that's an issue, because when ice melts, it increases sea levels. And when seawater warms, it also expands. So it's been said that about 80% of the increase in sea level rise is due to the expansion of the water, and 20% is from the water that's coming in off those melting glaciers that are on land. These large ice shelves breaking off, they can increase sea levels pretty rapidly. And there's supposedly Antarctica has several of them just anxious to hit the water and go for a good melt. And of course, another thing is freshwater is less dense than salt water, so freshwater wants to stay on top. So that can create some interesting effects in the ocean as well. Another tipping point is the albedo effect. Not sure if folks have thought about that, but when you melt the ice, then when the ice is there, it reflects sunlight back. But when you melt it, then 100% of the sunlight is absorbed. And that absorbed sunlight, the only thing it has left to do with all that energy, that 1,000 watts per square meter, is to warm up the water. And when that happens, more of the ice melts. And everybody knows that ice is melting up there. We actually have shipping lanes open that were not open 20 years ago. because of the ice in the Arctic melting. And so it's one of those processes where the poles are in the right half plane for the electrical engineers. Sorry, the left half plane. Anyway, bad deal. Another one, permafrost melting. What does that maybe do? Well, for one thing, there's a lot of methane in permafrost. So when you melt that permafrost, up goes the methane, and it's 20 to 100 times stronger than carbon dioxide. And the reason it said 20 to 100 is because initially in the atmosphere, it's much stronger than carbon dioxide, but within 10 or 12 years, it has decomposed into carbon dioxide and water. The CH4 breaks down in the sunlight, but when it first gets up there, it is a serious greenhouse gas. And so therefore, the more methane in the air, the more permafrost melts, and on and on and on. So this is a pretty serious threat. This is not the coronavirus here. This is plankton. And another thing that I never thought about a couple of years ago before I researched this is that, well, we all know that plankton are plants and they absorb carbon dioxide and they release oxygen, but they absorb a lot of carbon dioxide and release a lot of oxygen. And the warming is causing them to die. And that is not a good thing either, because it messes up food supply for fish. It disrupts the oxygen cycle. Nobody's really worried about going running short on oxygen, but this tipping point number 5 is actually eating away at oxygen, not a noticeable amount yet, because oxygen is 80% of the atmosphere, or 20%, sorry, nitrogen is roughly 80%. But still, it is something that's happening. And here's the key. 50 to 80% of our oxygen supply comes from those plankton. Number 6, transfer of ocean surface trapped heat to lower levels. Probably most people haven't thought about that. But anyway, this is another interesting issue that causes some interesting changes and messes up the environment. Number 7, loss of, I need to close my, loss of forests. Talk to the people in California, Oregon, Washington. And everybody knows forests eat CO2 and give off oxygen just like plankton. So again, I'm just clicking through because I mainly want you to notice what the particular tipping points are. And you can read the narrative underneath them at a later time, because we want to get on to the solutions here. Release of carbon from soils. Here are some of the pictures of California out west and so forth. When the soil is moist, it stores carbon, but if it gets hot, then it releases it, and that increases CO2, and so on and so on. And here's another one, 9 changes in major ocean currents. You know, it's kind of interesting. I'm sure we've got mechanical engineers in the group today, and you all know about coefficients of linear expansion and contraction. You know that the planet has these tectonic plates, and they're used to being able to move a certain amount. I mean, just a few degree change doesn't change the length of 100 feet very much. But when you're talking about planetary distances, thousands of miles, just a few feet change different in the expansion and contraction of something that is laid out over 1,000 miles. That can cause some serious things like earthquakes, for example. So changes in major ocean currents also affect weather patterns, and then crop yield, for example, depends on all of these things. Number 10, global pandemic. My goodness, I wonder what that might be. Never heard of a global pandemic before. I don't know, maybe some of you may have, but the point is, in this permafrost, folks are concerned that there might be some pretty nasty pathogens that paid good money a million years ago to get stored in freezing until they could find a time when they could emerge and do some good damage. And so what if there are some of them pathogens there? And who knows who those pathogens are going to affect? Animals, humans, whatever. Could be an interesting thing. We're pretty familiar with significant threats from pathogens over the past couple of years. So this is something to think about. What if we had one of these every year or two of something different that emerged from the permafrost? I don't think we want that. Number 11, total weight of rising seas and melting ice shifting. Well, we talked about that. All right, and here's the possibility of moving tectonic plates, okay? And nasty things as a result. So those are 11 points that some of which, and I'm guessing most of which, most people here haven't thought about unless you've seriously gotten involved. So let's see where the greenhouse gases come from. And of course, the finger is usually pointed at the electrical generation sector. Let's see what was happening in 2018. Well, 35.6% of the electricity in 2018 was generated with natural gas, 27.8% with coal, 17% with renewables, and that includes hydro, by the way, and 19.6% with nuclear. This is in the United States, okay? Now, where did the CO2 come from in the electrical sector? Well, coal was responsible for 65% of it, so it's pretty understandable why we're trying to eliminate coal from the electrical generation scenario. And 33% came from natural gas, which suggests that even natural gas is something we maybe need to think about. And then there's the 0.35 gigatons, 2%, 0.035 from other things like, for example, diesel generators, gasoline generators, and so forth. But coal and natural gas, they're the big time contributors to CO2 production in the electrical generation sector. In other words, if you're going to make electricity, 98% of the electricity made is made, and 98% of the greenhouse gases emitted by making electricity has come from the coal and natural gas. So, you know, that's a little hint that we need to focus on this. Where does it go? Who uses it? Well, the electricity sector. Now, this is the people who generate electricity. They use 37% of all of the energy used. In the United States, the transportation sector uses 28%, all that gasoline. That's 28% of the total energy we use. Industry, 22%. Now, that doesn't count the electricity that industry uses because that's already into the in that yellow pie slice, electricity, the energy that's used to make that electricity. So the 22% from industry is all those fossil fuels they use to heat up that whatever it is they're making so that they can turn it into something else. Residential and commercial, again, it's not the electrical use there, it's the other use, it's all those natural gas burning stoves and so forth. All right, 3%. There's other sectors out there, farming sectors and so forth. So anyway, these are the various sectors, and clearly if we could clean up electrical and transportation and industry, we'd have chopped off a significant amount of the carbon dioxide entering the atmosphere. So, and guess what engineers do? They kind of pay attention to all of these sectors because we're the guys who design that stuff. All right, so here's where we fit into this big picture. Where does CO2 come from? Well, it kind of matches up with the last picture. 28% comes from making electricity. 29% comes from driving around in transportation. 22% is the industry, what they're burning, which suggests they must be burning a fair amount of coal and natural gas. And residential and commercial, 12% there. So it wouldn't hurt to take a look at the residential and commercial, see what we can do there. Agriculture, take a look what we can do there for that 9%. Okay, so here's where here are the producers. Here's where it comes from, and so therefore this problem. And now that we've identified the problem, we need to start looking at the solution. But there are different sectors in the transportation sector. And it turns out personal vehicles are responsible for 58% of that CO2 production, large trucks, 23%, ships, air, rail, and others would be like farm tractors and so forth. So again, these personal vehicles and large trucks and maybe some of this other stuff, again, the target for the engineers and the architects, see what we can do about that. All right, let's look at worldwide consumption by energy source. A little history here. Notice that the fossil fuels are up there in the 100 quad per year range and have been relatively constant, increasing somewhat in the last few years, but not a whole lot. Notice that the hydro, that's the blue stuff, we're starting to build a little more hydro. The nuclear has actually been going down. And this is worldwide, by the way, not just the United States. But worldwide, nuclear is not as popular as it used to be, but folks are still building dams and building hydro. And but the real big ticket item here is the renewables, which is basically photovoltaics, wind, geothermal, and other non-hydro type renewable sources, with photovoltaics and wind being a large part of that. Okay, so what are we going to do here in the future? Are we going to go this way? And that's the red arrow, which says that would not be a good thing to do. The orange arrow says even staying constant is not a particularly good thing to do because we already know what that's going to do. So maybe we ought to follow the green arrow. All right, and so again, we're going to look at what we can do to try to follow that green arrow, see whether we can afford it. We already now know what about it, $1 trillion package that has just been passed that is government spending. So just take a look at it. And you know, this is what we're allowed to do as engineers. I decided, why do I have to listen to all these other folks? Why don't I draw some scenarios myself? So I decided I would do that. And here's what we have. We start in 2018 with total US CO2 emissions. And what we're looking at here is a situation where we don't change the energy, the CO2 production from the other sources. We only look at transportation, electrical generation, and industry. And we reduce it by the same amount every year until it's gone. And that same amount is 10% of the 2018 amount. And notice that that gets us over the hill by 2029, which now that probably more like 2030 or 2031 if we follow this scenario. But at least, you know, these are things we can do as engineers, especially if we like to draw pictures and graphs and stuff. So, and the math is pretty straightforward to come up with a picture like this based on those nice little pie charts we had. Okay, so now this is one scenario, but what if we say, well, maybe we can do better than that. So here's another scenario. And what this says is we're going to do a moderate 5% annual reduction in the other sources. So notice the blue one is getting a little bit smaller by 2029. Haven't changed what we're doing with transportation, like generation and industry, but acknowledging that some of these other sectors, like building better houses and more efficient commercial places, maybe we can knock off some more emissions by doing something like that. Okay, so scenario number 2, and let's look at one more scenario. And this is a little more aggressive. We're going to now reduce the blue ones by 10% a year. Each year is 10% less than the previous year. And if we do this, notice by 2029, we will have we will have eliminated 90% of the present CO2 emissions in 10 years. Now, nobody's even dreaming of doing that, knocking off 90% for 10 years, because who knows, maybe it's too expensive, whatever. Let's look at some numbers. All right. First thing we'd have to do to get that third scenario would eliminate coal. And we already know that coal is responsible for 1.15 trillion kilowatt hours. So that means we need to replace it with renewables or something else that doesn't emit greenhouse gases, but it just so happens that renewables are the most economical way to do that. Eliminate natural gas. And if we did that, we'd have to replace 1.47 trillion kilowatt hours. And as everybody knows, and especially was made public yesterday in Orlando, that we're going to need some energy storage to ensure the stability of our systems if we add renewables. And the amount is going to be somewhere in the neighborhood of 100 million kilowatts. So that's kind of what we need to do, the transition into renewable generation. So what's it going to cost? Well, in order to replace the coal, if you do the math, it's going to take around 716 million kilowatts of renewables. Okay, or 716, I guess that would be gigawatts, wouldn't it? If 80% of this is at utility scale, then that's going to cost about $1.72 trillion. And if 20% is at the residential scale, that'll be about $0.43 trillion. All right, this is based on some recent costs of utility scale and residential scale, and the numbers are realistic, at least this is what happened in Florida last year. 80% of the solar that was installed in Florida was installed by utilities and 20% by residential and others. So we're looking at a cost of $2.15 trillion or $215 billion a year for 10 years, and we have gotten rid of the coal. And I guess eliminated coal mining jobs, but certainly we've created an opportunity for all the coal miners to install solar. So, and maybe that's a little bit less dangerous, who knows. Eliminating natural gas using the same procedure. Bottom line here is $275 billion a year for 10 years. Now, how does this compare with the rest of the stuff? Well, we've already heard about trillions of dollars. The US gross domestic product is about 22.8 trillion a year. And get this one, the annual military budget is 700 billion a year. So for less than the spending of the military budget, we can replace coal and natural gas in a 10-year period. And not only that, we are talking about, this is government spending for the military budget. The renewables, that's not going to be government spending, maybe some of it for government buildings, government vehicles, and so on. But the big thing is a lot of this is going to be public-private investment, because investing in renewables is pretty good return on investment right now. So this is not government spending we're talking about. We're talking about, for the most part, private sector, maybe the government 10 or 15% of that. Okay, so we can afford it. That's the bottom line here, folks, is that we can afford it. And the nice thing about being engineers is we can do math and we can understand it. No, an architect. What about energy storage? Take a look at this picture. This is an interesting situation. This happens to be an energy storage out in the middle of the desert in South Australia. The Australians noticed that sometimes that wind power got a little bit erratic, and they need a little stabilization for that. So they thought, gee, maybe 100 megawatt plant that stores about 128 megawatt hours of electricity would be a good thing to try. Elon Musk got word of that and said, okay, here's the deal. We will install this thing in 3 months or less, and if we don't, you get it for free. It's there, as you noticed, and Elon collected his fee. And so here's what we've got, not just this big battery that Elon Musk installed in Australia at the end of 2017, but we've got pumped hydro. That's been around for a long time because, you know, we used to do that because we had excess nuclear at night. And it's so hard to cut those things back because they're pretty unstable and you got to watch them really carefully with those control rods. It's a whole lot easier to let those nuclears keep on going and build some big pumps and pump some water uphill and then let it run downhill. And it takes about a half an hour to reverse that direction and make electricity the next day during peak times. And there's compressed air energy storage, and that's been around for a while. Find yourself a nice cavern underground and pump some compressed air and then get it back when you need it to generate some electricity. There are double area capacitors, flywheels, at least 10 different battery technologies, electric vehicles, excess battery capacity. We'll take a look at that in a little while. And then something as simple as lifting cement or steel by a big crane up in the air and then letting it, grabbing onto that just like lifting an air conditioner up onto the roof of a 30-story building with a big crane or 20-story, whatever. And then that takes energy to do that. So use some of that excess electric to lift that thing up. And then at night, let that thing come back down slowly and get that energy back out and use it for nighttime electricity needs. So very similar to pumped hydro, except you don't need water much for it. And it doesn't take nearly as much space and probably can be permanent a lot faster. And in fact, the Europeans has demonstrated the commercial viability. So commercial implies cost effective. That's the issue here. And all of these things that we see in yellow above have been demonstrated for commercially. And they all have different purposes in the storage arena. Flywheels are not for storing energy overnight, but they are great for stabilizing the frequency of the utility grid and so on. So right now, storage is costing around $125 US per kilowatt hour. We learned from Orlando Utilities that, in fact, this is for installation, but for every kilowatt hour that you store, and you can do that every day, in and out every day. So if you've got a 30 megawatt hour storage facility, you can fill it up and empty it every single day. And so therefore you're amortizing that cost of those megawatt hours over the life of that system. And what it added up to, according to numbers presented yesterday by the Orlando Utilities Commission, was 0.7 cents per kilowatt hour of storage. So that's for stabilizing this electricity that the utilities are now making for about 3 cents a kilowatt hour. So, you know, it's out there, it's happening, and that's why it's happening, because it's cost effective, it's commercially sensible. All right, now one thing we need to recognize with storage is that there's a kilowatt and a kilowatt hour component, energy and a power component, or power and energy. And both of those are important, because when you turn on your electric dryer, you need 5,500 watts right away to heat that thing up, okay? But if you run it for an hour, well, it's not going to stay heating at 5,500 watts for that whole hour, but it might very well use 1 or 2 kilowatt hours over that time. So kilowatts and kilowatt hours are important factors that describe storage. We see that every day in our own business of installing a 10 kilowatt hour battery storage, which will have a maximum of about 3,800 watts of output. And so you need to look at both of those descriptors when you talk about energy storage. How much power can you get out of it, and how much energy can you get out of it? Okay, so a 1 megawatt and 1 megawatt hour means it delivers a megawatt for an hour. And this thing you see in the background here, this Australian system, is 100 megawatts and 129 megawatt hours. So that means 1.29 hours worth of 100 megawatts. And that gives the Australians time to get some other sources online. to back up whatever may have gone wrong. And if everything is going fine, then you can just back up for some of the any sharp changes in grid output. So here's pictures of some of the storage that might be out there. You can see the pumped hydro, that thing in the lower left-hand corner, that's a great big flywheel. And then we see a couple of batteries. The one with the flow battery is the one in the lower right, because that's the one that you don't want to get your feet wet if one of them leaks. So they got that walkway around it. And the other one, that's lithium batteries up there in the top right. How much? What's it going to cost? 4 hours of storage at 100 million kilowatts. Because that's about what we're going to need, supposedly, according to various projections. And again, we love to do the math. Okay, 4 hours, 100 million kilowatts, 400 million kilowatt hours, at $125 a kilowatt hour, $50 billion. Lots of money, but you know, compared to what we spend other money on, cosmetics, whatever, maybe 50 billion is a drop in the bucket. And as I pointed out earlier, this 400 million kilowatt hours is available to empty and fill every single day. Okay, and so therefore, great storage for at night and so forth. Got extra energy available, which now and currently and historically it's been at night, but now it's probably going to be during the day, and sometimes at night if the wind blows hard, because let's not forget about wind power, and let's not forget about some of these other additional renewable sources. I happen to spend my days on PV design and so forth, but we can't ignore the presence of wind and hydro, and well, hydro's there, it's been around for a long time, it's not increasing fast, but geothermal, places like Alaska and a lot of other geothermal hotspots, Iceland, for example, my goodness, they make almost all of their energy with just hot water that comes straight up out of the ground. There will be some short-term and some long-term storage. And the short-term is just minutes to an hour, and that's if there's an interruption in the source or even a cloud coming over a big solar farm. Longer term, 1 to 10 hours, takes care of it overnight. And it can be local, neighborhood, regional. It can be in your garage, as long as you protect it from being hit by a car. All shapes and sizes, or maybe the storage will be the car itself. All right, because here's electric vehicles, and what can they do? Well, they can do a lot. If we had 100 million EVs on the road, and if each one was able to contribute 5 kilowatts for 1 hour every day, that would be 5 kilowatt hours per vehicle, and that could provide 500 million kilowatts and 500 million kilowatt hours itself. I happen to own a plug-in hybrid that has 17 kilowatt hours of storage. I'd be happy to donate 5 kilowatt hours during peak time, especially if I got paid for it because of the bidirectional charging algorithm and a possibility of my car talking to the utility and negotiating a fair rate for providing that storage. So it's affordable. Again, the numbers are good. Storage is here to stay. And not only that, the costs are declining and the technology is evolving very rapidly. All right, let's talk a little bit about zero energy buildings. Just because I'm not sure everybody really understands what it means to have a zero energy building. Certainly it's not a building that uses zero energy. It's zero net energy. And here's the definition. You got this building, and it could be a campus or a community or whatever. It's just something you put in within a site boundary. And within that boundary, you've got some renewable energy production. And in addition to the renewable energy produced, if it's only produced when the wind is blowing or when the sun is shining, then you're going to need to supplement with some additional energy coming in from outside. And in order to have net zero energy, the energy that comes in from outside is going to have to be balanced by energy that's exported that will be renewable energy from your zero energy unit. So here's your definition of a zero energy unit, but this is a little bit subtle. There's a little more to it than that because we have to use source energy conversion factors. Oh, you know what? I have been going so fast, I have not looked to see whether there are any hold on here. Let's see if we've got any Q's and A's. No, am I talking too fast? Don't hesitate to type in a Q&A question, because I finally realized that I'm racing like a racehorse here. And with 36 folks, surely if there's anything I'm talking about that you want to ask a question about, we want to get that squared away and as soon as possible. So I'm sorry that I went on and on here. I guess I get a little excited about this material. But in any case, don't hesitate to type in a question. Happy to address them. So what's a source energy conversion factor anyway? Well, if you're going to make electricity with fossil fuel, most everybody, not everybody, but all technical people, engineers, architects, and so forth, know that you can only convert about maybe 1/3 of the heat that you create when you burn your coal or your natural gas or whatever it is you're making your electricity with for your boiler. And about 2/3 of that goes away. So in other words, it takes 3.15 units of primary energy to get 1 unit of electricity. Okay. So therefore, exported renewable electricity and electrons and electrons. So in order to be fair, we need to get, and especially if the renewable electricity displaces the fossil electricity, we need to give it the same conversion factor. Okay. Natural gas, on the other hand, if you're just using that for direct heating, it's about 91% efficient in a good boiler or whatever else you're heating up with it. You got about 19% losses with fuel oil, diesel, or kerosene, depending on what you're using them for. But again, we're using the heat from them, not the electricity from them. If you're using electricity from them, that's up there in the very top column. Propane's a 1.15, steam is a 1.45. You know, you boil this water and capture the steam, and you can use that steam to do things. Hot water 1.35, chilled water 1.04. Why should chilled water be 1.04? Anybody have any thoughts on why chilled water should be so low? I'm just going to look and see if I see anything pops up here in the Q&A. I am really concerned now. I'm afraid I put everybody to sleep. Well, perhaps maybe you need that rest. Well, I'm going to answer it myself. But please get ready for me asking questions like this, okay? Chilled water, of course, is probably going to be made through a refrigeration cycle, and they have coefficients of performance. So for 1 energy unit going in, you get more than 1 energy unit going out from the chilled water creator, whatever makes it. So therefore, the ratio ends up at 1.04. Coal, again, heating with coal, not making electricity, but you're just using direct heat from coal, conversion's 1.05. This is what folks have agreed on based on a whole lot of measurements of how efficient various equipment is. So using these source energy conversion factors, we can estimate, okay, here's a couple of Q&As. Let's see what we got. Thank you, folks. Let's see. Direct cooling, no loss. All right. And Eldon says I'm doing fine, so maybe it's okay if I'm talking as fast as I am. Appreciate that. A little feedback is always important. Feedback is what keeps things stable. So I'm going to click that I answered that live. I answered that live. So we'll move on to, thank you, Randy and Eldon, for your comments. Much appreciated. And now then let's estimate the direct building energy use here. Need a few more numbers. And again, this thing is that mechanical engineers and electrical engineers and everybody loves numbers. I can't imagine anybody not realizing and being thrilled to know that a kilowatt hour is equivalent to 3,413 BTUs if it's converted directly into BTUs, which is pretty much the case in an electric water heater. You got that heating element inside the water heater. There's not much else anywhere else for that energy to go other than heating the water. Therm is 100,000 BTUs. People in Florida don't necessarily know that, but folks up north tend to know that. Barrel of oil is worth 42 gallons, and it generally holds about 5,800,000 BTUs. And a gallon of fuel oil number one is going to have about 137,400 BTUs. Why do we care? Well, fuel oil number one is pretty common for heating buildings. So we kind of need to know about that. Okay, so somebody did something in the chat. I'm going to click on that. I'm not sure, but that should be just if you want to communicate with the host. Let's see, coal is better than natural gas or oil, and the conversion factor seems like it should be worse. Well, again, remember, we're just converting that coal to heat. So you're burning it, and it's a matter of how much of that heat you can capture. And these are not my numbers. These are numbers that come out of the US GVC, I think. So that doesn't say coal's a good thing either. It just says that's what you get for your conversion factor. It's good point. Intuitively, it does seem like it should be worse. On the other hand, it's a matter of how well are you capturing the heat from it. And I think part of it is that most of the coal now is not burned in residential furnaces, but it's burned in very large coal burning facilities, maybe at steel plants or something, where in fact, there might even be some waste heat capture. Just don't know the total answer there, but it's what folks have agreed on. But it's a good point. I appreciate your mentioning that. But next time, please also, Robert, if you'll put your comment in the Q&A. I'm going to be watching the Q&A from here on. Okay, so here's the conversion factors. What are they good for? Well, we have to convert all of our sources into energy equivalents using these factors. So let's do an example. Let's say we've got a dwelling that uses 7,500 kilowatt hours of electricity and 500 therms to purchase natural gas in a year. Okay, maybe this dwelling we're looking at here used to do that. Who knows? Anyway, perhaps another building will be built on this spot, and who knows, it might be a zero energy building for all we know. Hopefully we don't build back everything just the way it was. Hopefully when we start building things back, we'll build them back better. I believe I've heard that before, and listening to the various ads for the money the US government has just been allocating for infrastructure bill. All right, so here's our basic assumption. Let's see what it takes to do that. First, we have to convert the electricity to BTUs. So that's 25,597,500 BTUs for those 7,500 kilowatt hours. But that's direct conversion, okay? And now we got to use that special conversion factor, converting it to source energy by multiplying by 3.15. So that gets us up to 80,632,125, and I left out anything beyond the decimal point, okay? BTUs that we need. And these are the source energy BTUs, okay? Everything has to get converted to source energy. Natural gas, we got 500 therms, 100,000 BTUs per therm, times 1.09, that's 54,500,000 BTUs there. So the total is 135,132,125, and it's 0.617224, but I left that out. To get the source, so that's how much source energy we need. And if we try to do it all with solar, all right, then we have to figure out how much solar do we need to do that. All right, well, let's just do that. And let's see if it's practical. Let's see if it's doable, affordable, all right? So what about the size of that PV array? Well, typically, an unshaded south-facing array will produce about 1,500 kilowatt hours per kilowatt per year. Now, there's some parts of the country out in the desert where they'll go as high as 2,000. There's other places, they go down around 1,350. But people aren't doing only south facing anymore either. There are actually some north facing arrays being built because they are actually can be shown to be cost effective, even though they make only maybe 950 kilowatt hours per kilowatt per year. All right, depends on location. So let's use 1,500 as an average number. That would mean we'd need 5,119,500 BTUs per year per kilowatt. All right, because that's this 1,500 kilowatt hours converts to BTUs, and then we need to turn that into source energy. So we multiply by 3.15. So that means every kilowatt of PV that we install is going to give us 16,126,425 BTUs in a year's time. And of course, it does that every year, year over year through the warranty period of PV, and then it drops to zero. Actually, that's not true. PV has been shown to last a whole lot longer than it's warranted to operate. So in any case, in fact, you can't measure any degradation on a year over year basis just because the weather is not absolutely constant year over year. But anyway, here's our math. We're just doing the math here. We need 5 million. Let's see, what do we need here now? We need to have 135,132,125 BTUs per year. So every kilowatt gives us 16 million. So that means we're going to need 8.38 kilowatts on this house. Now, is that possible? I know at least one person in the audience who knows that possible, because this person has designed a house, put 40 kilowatts on the roof of the house. So 8 is peanuts, but let's see how much roof space it takes. 20% efficiency, that's about what arrays are now these days. They used to be 13.5 back when I first got into the serious PV install business back in around 2005. But now they're 20% efficient. That is 50% more efficient than they used to be. So the same roof space will now generate 50% more power and 50% more energy than it used to do. All right, now there is a limit. The maximum theoretical limit on silicon is up somewhere around 28%. So 20% is actually pretty good. Anyway, we saw the numbers earlier that the sun gives us about 1,000 watts per square meter under standard test conditions. So we're looking at 200 watts per square meter at 20% efficiency, and we need to have 8.38 kilowatts. So how many square meters does that take? Well, it takes about 42 square meters, which is about 450 square feet of south-facing roof space. 450 square feet, you know, gee, that's 10 by 45, isn't it? Or maybe 20 by 22.5, or somewhere in between. And of course, not too many roofs are actually square. They're going to have some oddball shape. But believe me, it is no big deal to cram 8,380 watts onto pretty much any residential situation. There's some that can't do that, but there are others. On average, it's pretty straightforward. Our average design these days is right around 11 kW. So 8,380 is doable, cost effective, and possible. So, and it's private investment for the most part that does this. Okay, there's some, sure, there's some incentive payments and tax breaks and so forth, but it's your money that you're spending ultimately. And the government investment is maybe 24% of that total, and the final 76% is yours. Okay, so if you're using 300 watt modules, and that's kind of a baby module now, most of the modules we use now are in the range of 380 to 440. So we got 28 modules, okay? And of course, you got to check the dimensions of the module to make sure they fit on the roof okay. And this sometimes becomes a very interesting exercise. So that's solar. There's your zero energy building. Now, there's more you can do. You don't just have to put PV to offset all the energy. Oops, there's another question. Let's take a look at that before we click again. Main issue is the HOAs. Oh, Scott, aren't you so right on that? You know, it's interesting. In Florida, we had passed a law way back. Back in the days of solar water heaters, that said, back in the late 1970s, it said, it is, you may not pass any laws to prevent the use of solar energy. In fact, the matter is that also applied to solar clothes dryers. You used to call them clotheslines. So yeah, but we, oh boy, very interesting to do HOAs. And Scott, you must be in the business. There's also a little interesting there's some other issues too, like building departments and authorities having jurisdiction. But we work hard to keep them all happy. And you're absolutely right. We have presentations have been made, not necessarily to the homeowner association, but certainly to owners in the associations. And we are breaking the ice here in Florida, and I'm sure that that ice is getting broken in other places as well. Because once somebody gets, usually what happens is the HOA requires the owner to take responsibility for their own roof. Because they're afraid it's going to leak. And what they don't realize is that solar installers install thousands and thousands and thousands of penetrations in the roof every year, and they don't leak. So in fact, in general, the only situation that I've seen where they've called solar people back because of roof leaks, it's happened that the roof is leaking someplace else. And actually, there are a lot of advantages to solar, but this is not necessarily to sell solar. Well, we can talk about that another day, but other than saying solar is cost effective right now. But Scott, thank you for that comment, because certainly anybody in the solar business understands exactly what you're talking about. All right, how about HVAC systems? Well, there's some interesting stuff out there. There's this one here. And this is a inverter technology heat pump. And this is basically a multi-zone mini split system. And once upon a time, heat pumps operated down to about 40 degrees Fahrenheit. And below that, you needed supplemental electrical heating. Now you can sit and have your morning coffee with a remote and set that heat pump to whatever temperature you want with an SEER up to 33.1. That is incredible. The very first energy efficiency building code I was involved with required an SEER of 8 as a minimum. So we have come a long, long way. Energy recovery ventilation, if you want to have humidity control. In other words, this is the counter-current heat exchanger. And as you bring in fresh air from outside and exit inside air, which oftentimes has smoke and other nasty stuff in it, it does a heat exchange operation. And sometimes that heat exchange involves condensation, where you're actually removing humidity from the outdoor air, hot outdoor air, as you're bringing it in. And so you need a drain on this thing, but these things are about 90% efficient. Pretty good for, rather than just having your infiltration around the windows and doors. Why not have a little counter current heat exchange? So very efficient. And not only that, these heat recovery and and energy recovery units have been demonstrated to also result in a more healthy living and working environment. Fewer colds, fewer all kinds of things. So I think we're going to see a lot more of these included in designs and incorporated into designs. And we certainly will see a lot more of these if those of us who are aware of them make sure we include those in our designs. Even domestic water heating, times are changing. Used to be solar water heater was the thing to do. No question, in Florida, that was a big deal. That's what got the Florida Solar Energy Industries Association going, was hot water. And they're still going strong, but now they're doing a lot of PV. And but solar water heater was a whole lot more efficient than reduced your electric bill, and the payback was great and so forth. But now it's possible to buy a heat pump water heater. And what they do is they suck heat out of the surrounding air, which means they act as an air conditioner. and they put that heat into the water with the CO coefficient of performance of about 3.5. So therefore, for every kilowatt hour of electricity you expend, you're getting 3.5 kilowatt hours of heating. Or in other words, the cost has just now been reduced by a factor of 3.5 of heating water with electricity. And when you start factoring that in to the use of the heat pump, here in Florida, we have a lot of temporary residents who live here 6 months out of the year. If they have a solar water heater on their roof, they're only taking advantage of it for 6 months out of the year. And the other 6 months, that hot water, it just stops, doesn't go anywhere. Whereas if they're making electricity with solar to heat their water and they're not using the electricity to heat water, then that electricity gets sold back to the utility. And so you've got 12 months out of the year benefit from the solar electricity, whether it heats water or not. So therefore, do the math, try it out, see how it works. And it's very likely you just might end up with one of these things. We are currently doing some renovations at our place, and all I need to do is find somebody from A.O. Smith or somewhere where I can find out exactly about the ducting, because my concern is in the Florida environment, I want to make sure that I can duct that cool air out of the space where the water heater is. Otherwise, I'm concerned about condensation from the cold air, get that area getting colder and water forming, and then comes mold. But these things are ducted. I'm aware of that at least, and it's something to look into, because I think a lot of this is going to happen. If it's in your garage, it's a no-brainer, because in the garage, these things, they air condition your garage for free. Another question, let's see what we got. Doug, okay, Asia has been publishing information about floating solar farms. 2.1 GW is solar, and even the floating solar farms overtaking the interest in wind farms and mass and public. I don't think it's overtaking the wind farms. The thing about wind farms is they are not linear. You know, the pressure from wind is proportional to the square of the velocity, and the force times the velocity is what gives you the power. So now we're looking at the cube of the velocity plus converting linear velocity to angular velocity. So you need fairly sustained winds, and you can't make wind energy economically everywhere, whereas solar is pretty much okay everywhere. Floating solar farms, yeah, they are definitely, the Chinese, of course, people talk about why should we be doing it here in the United States? Nobody else is doing anything. Well, wrong. Sorry, folks. China installed 4 times as much electricity, solar last year as the United States. They're the leader in the world in wind power. They're building hydroelectric like crazy. So China and India are really picking up and if we don't catch up to them, we'll see something at the end here. What happens if we don't start catching up to what's going on in China? In any case, the floating solar farms, they're talking about those in Orlando. They're talking about those in California. And indeed, what better to do with the sediment ponds from sewage treatment, for example. You're not going to turn them into swimming pools, but not a bad idea to put some solar panels on top. So yeah, that's happening. I'm not going to make a prediction, but they're certainly going to be coming on strong, because one thing that's needed for PV is real estate. There's a lot of free real estate sitting there on rooftops where there's not a whole lot else you want to do with them. But if you talk about land that might be used for farming or other things, then when you talk about the big solar farms, folks are talking about dual use solar farms. So at least you're not just making electricity or just not making wind farms for that matter. You see windmills with cows wandering around them all the time. So yeah, good point again, Doug. Appreciate your comment on that answer we did. Yeah, okay. So we are seriously considering one of these things installed at our place within the next 2 months. And one of these days I'm going to be able to hopefully go sit down with the dealer and figure out the best ducting solution. Okay. So what are the trade-offs? And the answer is, yeah, we don't have to just put in PV. There may be other things we can do, like put in more efficient appliances. They use less electricity, then we don't need as much PV. So again, do the math. What costs more? What's the most cost effective? And you have to talk about life cycle costs, of course, and maintenance costs, because we got to compare the overall cost, not just the upfront cost. And that may include the cost of the loan and the interest rates. You can look in different directions with PV, and we're going to take a look in the next slide what happens if you don't have south-facing PV. You can just make the array a little bit bigger because it's easy to simulate what the performance is going to be and install what you need. And then once you've installed what you need for your domestic use in the building, think about charging your electric vehicle, because that another 1,500 to 2,000 watts will charge your vehicle. Let's take a look at Q's and A's. I think I saw another one, did I? I gotta scroll this time. Okay, here we go. Doug, A's, you've been publishing information. Oh, stolen. Okay. Yeah. Yeah. Okay, we did. Do I see time for whether for the heat pump? It depends. You really need to talk about the marginal cost on that, not the total cost, because after all, you got to have water. And so you look at that over the life of the system. I don't know what the return on investment. I haven't done the math yet, but it looks pretty attractive. But with that information, I bet you could do that yourself and report back maybe. Thanks for asking that. Now I know exactly what I'm going to do after the webinar is over. I got to calculate the ROI for the heat pump. And thanks for asking that question. Okay. Optional array orientations. If we're looking at Albany, and I'll put this one in because generally most of the people attending these webinars are people who need live webinars. So, and they're usually up in the New England, New York area. So let's look at Albany. If you have an array, the phone will stop ringing pretty soon. If you have an array in Albany that's tilted at 30 degrees facing south, that is your best tilt for Albany. That gives you the maximum output for a stationary array, okay? We don't answer that phone because it's not ours. If you change the orientation from 30 to 45 degrees, you only lose 1%. If you change it to 60 degrees, you lose 7%. Okay, and these are all simulations that are easily done with a fine program you can download for free from the National Renewable Energy Labs called the System Advisory Model, SAM. So if you want to play with some simulations on your own, just go to nrel.gov and tell it you want to download SAM. It will ask you for your email and a few things because they need to prove that people are using their product because it's paid for with taxpayer money. But I'd strongly encourage anybody with any interest at all to download SAM because it's very intuitive. You can get simulations in the blink of an eye to tell you if you want to put in solar system that's facing at an angle of 302 degrees with a tilt of, with say a 412 roof tilt. It'll give you an answer and it's fast as you can snap your fingers. Just type in those numbers. So just look at all these different orientations. Looking southwest with 40-degree tilt, you lose 6%. Looking east with a 25-degree tilt, you lose 17%. So you have to install a little bit more. But at the price of solar now, you can afford it. Looking north, I didn't put north in here, but looking north in Florida with about a 412 roof tilt, you're down to about 70%. But people are even doing that because it makes them electricity from the sun. Some of this electricity is made by diffuse sunlight. You know, sunlight does come in the north-facing windows of your house. And in summertime, it comes directly in, but in the wintertime, it still comes in because it gets bounced around a little bit in the atmosphere. So it's just interesting to know that. Now, if we look at the additional cost to build a zero energy building versus the savings in energy bills in 6 different United States cities, folks did a study on this, and here's what they came up with. It's really, really interesting because for an initial investment in Atlanta of $19,548.22, you can save $152.03 on your electric bill every month, and your mortgage increases only by $99.99. I rounded them off. Okay. So you're saving $52 every single month from the start until your mortgage is paid off. And if your mortgage is paid off in say 15, 20 years, your system's still going to keep on going. And then it's free, totally free. Look at Baltimore, Chicago, Houston, New York, San Francisco. San Francisco, big savings because San Francisco has kind of expensive electricity in the first place. About the same investment, we're looking in the range of 18,000, but now you're saving $217 a month on your electricity versus an extra mortgage payment of $91. So, you know, how can you go wrong when you've got this kind of economics looking you straight in the eye and saying you would be really silly not to do this? Well, a lot of people are going to doubt it anyway, but here's the math, here's the results, legitimate studies. It is really worth it now to carefully design a zero energy building, paying attention to envelopes and all kinds of other stuff. All right, so what about retrofits? Sure, there's millions of buildings out there, and a lot of them can be made greener. All right, all this stuff to do. I'm looking at my clock here and see how we're doing. Now 11:23. Oh, we're gonna make it. Better doors and windows. You know, there's a lot of benefit to better doors and windows. We just put in hurricane glass in our entire building. We live in a condo when we're there. Right now we're having renovations done. We don't have a kitchen. We don't have bathrooms. We don't have bedrooms. So we had to move out of the house. But in any case, previous to that, we had installed all hurricane glass, and I was expecting, great, now the hurricanes won't blow the windows out, but it's a whole lot more than that because it's sound insulation and they are installed much more tightly, so there's less infiltration. So better doors and windows are not just energy savers, they can do a lot of other good things. LED lights, refrigeration, all these things, they're so much more efficient now. Plug up those air leaks and put in the energy recovery units if you can. Air leaks, that's 100% loss. Energy recovery, 10% loss. Pretty big improvement. Upgrade the insulation, but you can go too far on that. Pay attention to every time you double your insulation thickness, you cut in half the amount of energy transfer through, but you reach a point of no return. Done the math on that one here in Florida, anything over R19 in Florida is a waste of money because the attic's temperature difference across the attic is not that large. The amount of energy saved, it's better put that money into a more efficient air conditioner or something else. So that's the kind of exercise you need to do in order to make sure you do the right thing. I mean, you don't have to do that. It's your money. You can spend it any way you like. But if you want to spend it more efficiently, we're lucky as engineers. We can do the math. We can figure out what makes more sense. Even landscaping and in some of these time clocks and some of the new energy management systems that are part of smart buildings, water clocks that even pay attention to how much shade is on your lawn. and water the shaded parts less. Uh, Lots of cost effective. These are all things that are in the market that we can buy right now, and they are cost effective. You can compute the energy analysis. Here's the Energy Gauge USA that's out of, and you can see this is trial software here. You can run it for a week, and you find your location, build your building, and Energy Gauge USA is not the only one out there. Point is, if you want to do energy efficiency, you don't have to guess anymore. You just put the information in, and they analyze the building envelope, building equipment, and the cost effectiveness of whatever it is you want to do. So again, you don't have to guess. Just put the numbers in, garbage in, garbage out. Put in good numbers, and you get good numbers out. NREL has building energy or BE-Opt. Florida Solar Energy has Energy Gauge USA with 2 versions, and there probably are other things out there as well, but these are 2 I'm aware of that you can download for a 30-day free trial if you're interested in trying this, and especially if you want to do it on your own unit. What could be better than a 30-day free trial to do some calculating to make your own building more efficient? All right, and Sam, I already talked about NREL, Sam. If you want to do some PV, it's a great way of analyzing what you might want to do. Now it is time to talk about vehicles, because as you noticed earlier, vehicles use a lot of energy, and engineers have an association with vehicles. Some of us design them, but most of us who are PEs drive in them. And a lot of the engineers who design the vehicles are not registered PEs. They work for large companies, but they're still engineers. And let's take a look at some vehicles here. Let's look at some numbers first. Again, everybody loves numbers. Every gallon of gas that gets burned dumps another 19.6 pounds of carbon dioxide into the atmosphere. Okay, and you don't have to memorize these, just order the slides and you get all these numbers. Coal generated electricity, 2.2 pounds for every kilowatt hour you make with coal. Natural gas, 0.9 pounds. So they talk about clean burning natural gas. It's a lot cleaner than coal for making electricity, but it's not a 0. And renewable, that's 0. All right, once it's installed, it operates for years and years and years, and no CO2 generated. Now, if a gas car averages about 25 miles to the gallon, then it means if they drive 100 miles, they're going to dump 80 pounds of CO2 into the air. And electric cars get 3 or 4 miles per kilowatt hour, and then ours happens to get 4. And most of the other owners I know get about 4. And therefore, if electric cars using natural gas generated electricity, that means they dump about 25 pounds of carbon dioxide per 100 miles driven, rather than 80 pounds. That's pretty big savings right there, isn't it? Now that's if the electricity is made using natural gas. If the electricity is made with solar, then it is 0, zip. So that's it. Solar electricity, charge up an electric vehicle, which requires less maintenance than a traditional gasoline-driven vehicle. And I've got 3 years of repair bills of missing repair bills to confirm that. So, you know, I asked, do I really need an oil change? I rarely use the gasoline engine in the car. They say, yeah, you do. It gets kind of old in a year, and you don't want to get. So yeah, you still need an oil change once a year, even if you don't burn any gas. So this is, for me, this is really exciting, and I hope that you'll feel a similar way. Here's another question. Let's take a look here. Q&A number 6. Age of, okay, move down. Do I have any data on hybrid vehicles? Yeah. Maybe you might be a little more specific. You're saying how much, I have another presentation on that covers this in gory detail, but the hybrid vehicle typically gets about 50 miles to the gallon. So if it's not a plug-in hybrid, then it's a gas burner, but you need to treat it as a gas burner. Gets around 50 miles to the gallon, depending on, and you know, depends how you drive it and which one it is. Hybrids are a fine transition vehicle. We owned hybrids for 10 years before we got our plug-in hybrid, actually more than 10 years. And we were sold on hybrids because they're pretty nicely performing vehicles. So that is my answer. If that is not good enough, be a little more specific about what data you'd like to have. Okay. So, oops, click the X. So there's the numbers. And now let's look at a comparison. We're going to compare an EV at 10,000 miles on renewable electricity with and see what that does. Well, there's no CO2 release. You're talking about 15 cents a kilowatt hour for the electricity, depending on where you are. And this varies a lot because we live in a commercial type building, a condominium, where we're on a demand rate, a general service demand rate. And that means we pay for demand and we don't contribute to that because we only charge at night, but our rate per kilowatt hour is only 8 cents. So that means we drive our car for 2 cents a mile, whereas it's more than 10 cents a mile for gasoline vehicle, typical again. So we're looking at fuel costs of $450 for driving 10,000 miles at 15 cents a kilowatt hour. Okay, and half that for us driving 10,000 miles, which we don't do anymore anyway, more like 5. No other emissions, no carbon monoxide out there, no nitrous oxygen, no nitrogen oxides, no sulfur oxides. And furthermore, the batteries in the EV are available for utility storage when we finally get into the mode of bidirectional utility charging, which we're almost there. Tesla is ready for it. Let's look at a gasoline vehicle. Same thing. Typical gasoline vehicle, 25 miles per gallon. If you got a 50 mile per gallon hybrid, cut these numbers in half. 400 gallons of gasoline, it's about $3 a gallon, $1,200. Well, now gasoline is now more than $3 a gallon down here in South Florida after that little issue down after the hurricane. So I don't know what you're paying up north for. I don't know much about what people are paying for fuel here either. I see signs. I think it's now $3.50 a gallon. So, but it fluctuates a lot when an electrical cost doesn't generally fluctuate that much. 7,840 pounds of CO2 released by that 400 gallons of gasoline. That's 3.56 metric tons, by the way. There's 275 million of these things on the road right now. So that means 2.16 trillion pounds of CO2 released every year by our vehicle fleet. We can change that. More Q's and A's. Let's see what we got here. Okay, moving on down here. Any data on hybrids? Okay, so how about half the gas engine? You're talking about, you mean a gasoline engine that gets 50 miles per gallon? You just cut these numbers in half. But the average mileage for the vehicle fleet is in the neighborhood of 25 right now. I think, Scott, maybe that's what you're talking about. I'm not sure. And by I see that Scott's had a number of comments here. If any of you want to carry on this dialogue after the meeting here this morning, I'm telling our host that he's welcome to give out my my email if you want to contact me. Okay. Yeah. Okay. So as you can see, we have a problem that can be solved. There's a chat. What do we have in the chat? Consider most EV charging jumps on the grid. No, I do, exactly. That's the thing. That's why we had a previous slide that showed that if your EV, most of the grid electricity now, depending on where you are, utilities are switching over to natural gas. So you're looking at about 0.9 of a pound per kilowatt hour. And that was included in a previous slide. We can we might have time to go back there later, but order the slides, and the first comparison of the electric vehicle charged with utility electricity made with natural gas shows what the comparison is. And if I remember, it was something like 20 pounds compared to 80 pounds, about a 75% to 80% reduction using utility generated electricity rather than gasoline. Okay, but the numbers are there in a previous slide. Okay. You know, we don't just travel by automobile. There's school buses. Florida got a settlement because of some bad practices that Volkswagen made with their diesel, and they're buying electric school buses. And here's a regular downtown bus that Lion's making that's all electric. Truck, electric truck, transport truck. Can you imagine if all those prime vehicles that are on the road now were electric? And in one of these days, they probably will be, because they're going to find out that that's pretty, while they're loading up, they can be charging up, and off they go. What else we got out there? Oh, there's this one. Anybody know what this is? Go ahead, hit the Q&A if you know what this is. The first one to answer gets congratulated for being the first one to answer. I'm watching. As soon as that Q&A turns to 9, I'm going to click on that thing. What is this strange looking creature down the lower left-hand corner of the picture, of the slide? Oh, here's a couple of them. All right, we got 10 and 11. What do we got here? Tesla truck, solar panel car, cyber truck, Tesla pickup. You're right, it's the Tesla. And congratulations to all of you. That's what I promised, right? I didn't promise any money, I don't think. But congratulations, because that means that somebody's been paying some attention to what's coming up out there. Okay, what else we got? Oh, then this is electric crane. And these things are out there now. Can you imagine what's coming beyond these? Well, you know, there's still more out there. There's small stuff. There's this cute little electric bike, and this cute little electric transporter. I believe this is, if you go to India and a lot of the countries over in Asia and Africa, you see a lot of these. And if this is electric, my goodness. That's a cute little thing, no CO2 there. Electric motorcycle. Can you imagine? I mean, I don't know whether Harley made this thing, but when you get in a Tesla and you see what that thing can do when it's next to a muscle car, leaving them back in the dust, imagine what this motorcycle must do. I don't ride on motorcycles, but I can just imagine what this thing must do. And of course, then there's just plain old van, but it's a small one. It's a cute little thing, and all electric. So this is out there right now, folks. Let's see, any of these 13 in here that I didn't catch. I lost track. Okay, there we go. I got to remember where we leave off here on the questions. Okay, so where are we going next? Well, here's that cute little BMW. I always kind of wanted to get one of these. How much additional renewable energy do you need to power 275 million of these rather than the 275 million gas-powered vehicles? Because we didn't include this in the calculation earlier, did we? adding the extra EVs. So let's take a look at what it takes. About 4 miles per kilowatt hour, 10,000 miles a year. Not a bad assumption there. Okay, so that means we need to have 2,500 kilowatt hours per year per vehicle, something in the neighborhood 688 billion kilowatt hours per year for the fleet. All right. And we already know the costs on replacing coal and natural gas for 1,634 billion kilowatt hours. So that means it should cost about $1.3 trillion to charge every single electric vehicle that has replaced all of those gas guzzling vehicles with electric vehicles powered by solar. Another 1.3 trillion. So, you know, that's 1.3 trillion, a one-time cost too. If you spread that over 10 years, whatever, it's getting down in the noise important in terms of what we spend money on. So it's affordable. We know that a kilowatt of electricity is going to produce about 1,500 kilowatt hours per year. So of solar. So how much extra solar does it need? Well, you need 2,500 divided by 1,500, roughly. Let's just say 1,250. A 2 kW solar array will keep your electric vehicle charged all year long. Of course, that assumes you're going to plug it in during the day. But let's put it this way, it'll make enough electricity to keep it charged. And in fact, if your car gets charged at work where they have that solar charger powered by the sun, of course, then maybe this is actually a pretty realistic expectation. Not half bad. I mean, if you charge at level 2 about 6,000 watts or so, you can charge at about the rate of about 25 to 30 miles per hour of electricity put in the tank. So if you're at work for 8 hours on a charger, a level 2 charger, it makes all the electricity you need to get to and from work in the day, and during the day while the sun is shining. Okay, so not a bad deal. 130 billion a year over 10 years. Now, this is ballpark because, you know, we may not have to build that much additional electricity, although if the population continues increasing, then the demand for electricity might go up, or who knows what's going to happen as things get more efficient. But we may not need to build as much electricity as we thought to do all this charging, but we know here, we can see here that certainly the economics are favorable for building this. So, whoops, here chat came in. Let's see what's there. We're not seeing what you're looking at. Steve, I'm not sure what you mean by we're not seeing what you're looking at. You mean the questions I'm looking at? Or are you not seeing the slides? That's pretty important. I've got the impression that everybody sees the slides, or I think that the chat would fill with people saying they can't see the slides anymore. But I'm just looking at the Q's and A's, and if you click on the Q's and A's on yours, you might be able to see them. I'm not sure. Okay, let's see. Here's chat again. Let's see what we got. Oh, I got it. Okay. All right, good. So, important to know, what do we need if we want to power all these EVs with the renewables that we didn't include before when we were just talking about the buildings? So what happens when you adopt renewables? What happens to the grid? Well, there's a couple things. One is you need more, they're less predictable, so we need more storage, and we hinted at that earlier. All right. But with electric vehicles, we can do a lot of storage. We can do like 600 million kilowatts and 1 billion kilowatt hours. So just EVs alone can make a big, big difference. There are concerns from the grid standpoint. if there's too much power on the grid, and we've come across this in one of the larger projects our firm has done, they do a study to see how much it's going to affect the grid and whether any of this grid, any of this electricity that we generate and dump into the grid is going to find its way back to the generator, because generators, rotating generators, do not like for electricity to be coming into their terminals, because then they want to pretend that there are motors. And that is totally opposed to the idea that they want to be running in the forward direction and making electricity. So that's one of the concerns, but it's easily solved because it's easy to measure what direction the power is going and to do something about it. There's concern about voltage amplitude stabilization at substation levels. And well, again, we're finding that for the kinds of PV we're looking at right now, that's not a big deal. But it is also, the concern is if the voltage taps on the transformers at substations move up and down more than they're designed to do, that they'll wear out faster. But there are some really sophisticated electronic solutions to this that are available right now. Imagine a high voltage DC transmission line converting first AC to DC and then DC to AC again. If we can do that in terms of power electronics, then a substation ought to be a piece of cake. So I wouldn't be surprised to see some of these things happening within the next 5 years. The power engineers are going to start doing that. Well, okay, so what's going to happen to the grid? Let's look at the question. I see, I think another one came in here. Have I looked into thermal storage? Eldon, I haven't personally looked into thermal storage, but I know that folks are talking about thermal storage like out in California. I think you're talking about maybe these solar mirror systems that heat and they have liquid sodium that they store underground. And then they use that to make electricity. I believe that may be what you're hinting at, that kind of thermal storage. And I haven't looked into it in terms of the economics, other than the only thing I've looked into is that they're certainly thinking hard about it. And it certainly is, it appears that it's going to be another very viable way of stabilizing the grid, and particularly at night. So if you want to comment that maybe you've had some experience with that, I'm sure we'd love all to hear about it. You can type it, or we'll see how things go. Maybe let's see. Well, we're at 11:48. We're close. We're close. So if we have time at the end, we're going to go back and we're going to talk about anything anybody wants to talk about. Hopefully, we have stimulated some thought here today. That's the whole purpose. Let's see the slides. Okay, here we go. So the question is, all these things we're talking about, what happens, what's it going to do to the grid? Well, let's look at what the grid is right now. We make electricity, it's transmitted through some high voltage transmission lines for who knows how far, maybe a few miles, maybe a few hundred miles. Guess that's at somewhere in the 138,000 volts or more. Goes to substation where it's distributed to neighborhoods at somewhere in the neighborhood of 13,000 volts. And in that neighborhood, you're going to find transformers that are serving buildings that have loads. You're going to see transformers that serve big buildings that have big loads, and that's mostly what's out there now. Is that one directional power flows from generator to the user. Now that's mostly what's out there now, because there is a lot of solar out there. And fact of the matter is there's a lot of wind coming on and other kinds of generation other than that generation in that salmon colored box on the left hand side. So what's going to happen? And what I say, what's going to happen? No, wrong question. What is happening right now before our eyes? And this is what's happening. start on either end. Let's start on the right-hand side though. Start a big building. Probably has big load, transformer connected to the utility, and maybe a little bit of PV on its roof. Small, I'm saying maybe 50, 100, 150,000 watts. Most recent commercial job we did was 130,000 watts. They didn't have any small storage, but the small storage might want to be in the neighborhood of, say, a couple hundred kilowatt hours of storage to get through a few hours of outage maybe. And then we're looking at a residential situation here where some residential will just have small PV that contributes to the reducing their load, and anything in excess goes to the utility. And then there's the one in the middle that's got a little bit of storage with their small PV system. And so they can save some of their electricity to use either during peak load times, or to sell back to utility during peak load or whatever. And then there are going to be a few of these folks out there that just decide, I'm going to put in a power wall. I don't have room on my roof, or I got too many trees around my house to install solar, but I'm still going to do some energy storage. So in case I've got an outage for a couple of hours, that I'll have some electricity to solve that problem. So there we got the residential picture, and then we go to the substation. And the substation itself, no reason why you can't put some storage on site at the substation, like something in the order of 30 megawatt hours or so. And there's no reason why it is, well, other than space, might be a possibility of including some slightly larger size renewables, like say half a megawatt or so. And then we get at the transmission voltage level, where we need a bidirectional link, because here is where this bidirectional link, you see the arrows are going both directions at the input to the substation. We need to make sure that none of that power that's going towards the generator gets used, discourages the generator. So we got to dump it into into that big storage tank that's there at the bidirectional link. But then when we need it, there might be a big solar farm out there too, 100 megawatts. They're out there now, lots of them. And in fact, 80% of the solar built in Florida last year is mostly big renewable stuff. So this stuff is there, more and more coming on all the time. So that's where we're headed. And you know, we're all going to be a part of that, whether we like it or not. We might as well be a part of it and like it. So let's see, what do we got here? We got all 16 of these. We've got all 16 of these, indeed. Okay, wanted to make sure, because we want to talk a little bit about leadership. What's the government going to do? And let's don't forget that we are a part of the government. It's our input that hopefully we small guys, if there's enough of us, we can make a difference in what the big guys do. But we can make greener government buildings, greener government transportation, greener incentives for green economy. One of the best ones I've heard is, you know, rather than the investment tax credit that all the people who pay income tax, why not just a rebate, straight rebate to people, so people who don't pay a lot of income tax and still put in PV and get an incentive for it? Or what about the nonprofits who don't pay income tax? There's no particular financial incentive for them to install PV, other than somebody who is in the business of installing PV on the roof of nonprofits and charging them for that electricity. So there's interesting things there. Electric vehicle chargers at government buildings, what a good idea. Green the military. Military is already doing that. They understand that they can operate more efficiently and better, but they're green. Planning, development, local levels. A lot of industries don't like anything to have payback more than a year and a half. So there need to be more incentives probably for commercial and industrial green investment. And one of these days, we're going to see the building code change to strict zero energy, because it's going to be more cost effective to go with zero energy than to go with the wasteful buildings. So it's on the horizon. Where does our money go? Well, some of the big lenders lend a lot of money to the fossil fuel companies. If you don't feel right about that, you might want to think about this. And there's other lenders who don't invest in fossil fuel. Again, I'm not telling you what to do, it's just presenting information because it's interesting of who is serious about cleaning up the planet and who is more serious about just hoping to make lots of money. Now, here's what I was been hinting all along is what is the effect on the gross domestic product? With either we don't do anything, we're just doing a scenario of business as usual, or we take aggressive action, which would be defined as what's coming out of the climate accords. Okay, and here's what this is work that economists have done. All right, and where was this found? This was in Scientific American, November 2019. I consider Scientific American to be a pretty credible publication. And look what the results are. The blue is if we go green, that's the effect on the economy. And this is per capita GDP, so that's kind of a secret. You got to be careful with whether it's the total GDP or the per capita GDP. But the world not going green, serious effect. Rich countries, serious effect. Less effect on the poor countries. Hot and cold countries, both fairly serious effect. Look at the United States, though. My goodness. I mean, no matter what we do, it looks like we're going to reduce our per capita GDP. But if we don't do something, compare the United States with China right next door to it there. All right. And China is on the road to doing the green thing. And you can see what's happening. Their economy is actually increasing. Their per capita GDP is actually increasing as we go. And we're looking at 2030, 2050, and 2100 as the dotted lines there. So by 2050, China, by going green, I mean, why would they not do that? Well, it's clear. Why would the United States not want to go green when we look at these kind of economics of not going green? And you start doing a cumulative difference in per capita GDP. And I made a mistake here. I'm not sure whether I corrected it into per capita GDP. But the point being, we're looking at $68 trillion over that period up through 2100 if we don't invest in going green. And we're going to be behind everybody else on the planet who's going green. So you got to think about it. Who's most significantly affected? Boy, the farmers really got nailed. Agriculture lost $2 billion in Nebraska alone in 2019. Infrastructure, flooding damage. All right. Other effects of not going green here. Forget, we're talking about our food supply. And finally, what about some greener ethics? This looks like a nice solar farm out in the middle of nowhere, doesn't it? This happens to be a big utility scale solar plant up in the middle of Minnesota in the wintertime. That was built by Xcel Energy. And what might be greener ethics? After all this, anybody needs ethics credit, does get some ethics credit for this presentation. And the idea is that the design professionals need to adopt saving the planet as a primary canon in all the codes of ethics. Civils have done it. I haven't seen all the codes of ethics, but basically engineers are getting on board and catching on that we have some responsibility here, and it's an ethical responsibility. And isn't it nice when the ethical responsibility matches up with the chance to earn an honest living as well? Here's another question came in, a comment. My example, why does determining size of PV array depend on converting source energy? The array would be independent of the utility power plant's inefficiencies. Okay, the point with the source energy is we're talking about eliminating fossil fuels. So what we're comparing here is how much fossil fuel is eliminated by going with PV. And every kilowatt hour of electricity we can make with PV avoids the need to make that kilowatt hour with fossil fuels. And we're assuming we're using this kilowatt hour efficiently and and actually replacing the fossil fuel, which is ultimately going to happen. And so that means that since the source energy is 3.15 for the utility made electricity, meaning that it takes 3.15 times more basic energy, source energy, coal, BTUs, to make 1 BTU's worth of electrical energy. So that's why they do that, is to make sure that we're comparing apples with apples. And since we're talking about electricity and electricity, the PV gets the same source energy factor as the utility generator electricity. Okay, and I think I mentioned that back then, but certainly worth mentioning again. Where'd my cursor go? Oh, there it is. Okay. Moving on here. Reducing carbon dioxide. People have to go have jobs to do this. They get paid. Supposedly, if it's a good job, you get paid for it, and then you can contribute to the economy. And I mean, our company has doubled in size in the last 9 months, maybe more than double. And we're just an engineering group. And you know, the amount of plans that we can generates an awful lot of jobs for people in the installation business. So there's lots of good jobs out there, and nice clean energy. People feel good about what they do when they go home at night. So here's what we need to do, folks. We need to convince our clients that it is cost effective to go green. We've got the numbers here. Let's have these numbers available when somebody says, "Ah, that's too expensive," or "That takes too long." How long does it take to install a PV system? Depends on the size. About 3 days. You got a good crew out there? No, I'm sorry. I mean, there are no good reasons for not going green right now, other than you hate the planet. I suppose that might be one. But anybody who wants to leave the planet an inhabitable place for great grandchildren needs to get serious about thinking about these things. My opinion, of course, but then again, I think there's a few 100 million who agree with me around the planet. So what else do we need to do? Well, there's more to it than just reducing energy costs. There's so many other things that we've greened up, including healthcare costs and a lot of other associated costs as you read through what these various things do. Today, we're just about done here. It's 12:04. In fact, we are done. So we just don't have time to talk about all those things, but there's more to it than just reducing the CO2 emissions. And now's the time to do it. And here's some reasons why. And I guess I've mentioned them all before. The thing that gets me is I have a sign right in front of me that says, when all is said and done, a lot more is said than done. And we need to get busy and start doing it. Okay, so let's go up to Q&A, a couple more comments here. Okay, here we go. Richard wrote your town's climate action plan, green fleet policy. Richard, congratulations. Let's see, what do we got? No longer work there. However, you're actually attending town council meeting. Oh, heavens no, there are no copyright issues. You are welcome to download this thing. It'll be in PDF format, but I would consider that a compliment if you were to use this to educate other people. We are talking about crisis issues here, and if I start worrying about copyright on this presentation, then the whole thing would be hypocritical. So anybody wants to share this with somebody else, you are welcome. There are lots of references within it. Best of my knowledge, everything is factual. Most of the numbers and calculations are mine. I may have missed some decimal points, but I've checked them carefully. If you find something wrong, tell me about it. We'll fix it. Okay, let's see. Direct cooling, no loss, was relative chilled water at 1.04. When is it used for cooling? Oh, well, I mean, there are some systems out there where chilled water is the cooler. They don't use compressor. They chill the water and run it through the building. I'm familiar with an older building in Kansas City, Missouri, where they do that. I'm not sure what other uses, but chilled water oftentimes goes into air conditioning. That was some of the earlier ones. All right, let's see, a couple of thank yous. Oh, I love that. The inconvenient truth. Al Gore probably appreciates your saying that. But you're absolutely right, Dan. The numbers look really good. There's no question about it. I don't think we could argue that our small company of a half a dozen engineers has done 1,600 residential systems in the less than a year. Something's got to look good about it for the people out there selling it, because there's no way we would have done that kind of business in this kind of year. So thank you so much for your comment there. Much appreciated. And ladies and gentlemen, I appreciate you all being here this morning. I hope you got found it to be worth your while. And like I say, if you want to chat anymore, I'm always happy to email back and forth. The host has that, and you can get it from him. For that matter, I guess I could, well, I'll just suggest get it from the host. Okay, 3 chats. Let's see what the chat. Don't reply. Okay, yeah, that's from the host. Okay, folks, thank you very much. Enjoy your lunch, and I hope you have a great holiday season. I'm gonna